this problem is very similar to a problem on the exam, so pay close attention, and I would use it to study, like the night before or whatever, go through it again. And here's what you're given. We have a football that's being kicked off on a flat football field, and it's launched at an angle of 50 degrees to the horizontal, moving at a velocity of 20 meters per second. Part A, and here's A right here, what is the initial velocity in the x and in the y directions? Part B, which is at the very, very top of its height, what is delta y max? Here's delta y max up here. And how fast is the ball going at that point? And how much time does it take to go from the bottom to the top of the flight? And then for part C, right here, just before it hits the ground, what is delta y? How much time did it take to go from here over to here? And what's delta x? And I forgot to draw that. Delta x is from here to here. Sometimes in a projectile motion problem, that's called the range of the flight. And then, and how fast is it going? And I'm going to put a vector hat on there because I want an angle as well. So let's see how this goes. Let's solve it. So let me zoom out a little bit. And if you're watching this online, pause the video and try to do it yourself. Okay, part A. These are just the x and y components of the initial velocity vector. So here's my initial velocity vector, and so here's the x component, and here's the y component. So this is really v naught x and v naught y. Well, I know the hypotenuse. This makes a right triangle. Whenever you take a vector and break it up into its x and y components, you will get a right triangle because the x component and the y component, by definition, are at 90 degrees to each other. So you've turned this vector into a right triangle. And v naught x, well, this is the adjacent component. And when you want the adjacent leg of a right triangle, you multiply the hypotenuse by the what? By the cosine of the angle. Now, by the way, here, listen to this. We use cosine theta here, not because it's the x component, but because it's the adjacent leg of the triangle. That's what defines cosine. Most of the time, when you take a vector and break it up into its x and y components, the adjacent component will be in the x direction. But you remember in the inclined plane problems that we've done, that x and y kind of get reversed when you're breaking the gravity into its x and y components? So don't think of it as cosine being x. Think of cosine as being adjacent. Look at the triangle, let the triangle tell you what to do. So this is going to be 20 meters per second times the cosine of 50 degrees. And this will be equal to, well, let's see, 20. Let me, 20, come on, turn it off. Turn my calculator on first. 20 times the cosine of 50 degrees is my calculator in degrees. Yes, it is. Equals, and you get 12.9 meters per second. Now, v naught y is just the same thing, right? 20 meters per second. But look, v naught, that is the opposite leg of that right triangle from this angle. Opposite from this angle. Look, see, we've got to go over there. So therefore, you use sine. You use sine when you want the opposite leg. Sine of 50 degrees. So 20 times the sine of 50 degrees, and you get 15.32, or 15.3. And we're done with part A. Boop, boop. We got those. Now for part B, delta y max. Now here's what you have to understand in order to get this problem. You have to understand that what is true about the velocity at the very top? What's that? Yes, exactly. The y component of the velocity is 0. So if I say this, well, so what do I know? I know the initial velocity in the y. I know the final velocity in the y is 0. And I know what the acceleration is. What's the acceleration in the y direction? Negative 9.8. Now I don't know time, and I will find it later, but I don't need the time to find delta y. I'm going to use the fourth kinematic equation. Vy squared equals v naught y squared plus 2a delta y. And just solve this for delta y. Remembering that, oh, my final velocity in the y direction is 0. So I'm going to take this and solve it for delta y. And I'm going to do it in one step just to save some room. So delta y is equal to, well, I'm going to subtract this to the other side. And that's negative v naught y squared over 2a. Now I'm going to plug in my values. So delta y is equal to negative 15.3 meters per second squared divided by 2 divided by negative 9.8 meters per second squared. Now notice that this negative cancels this. That makes sense, right? Delta y is going to be positive. It's going to be up. And so I'll say 15.3, square that, and then divide it by 2, and then divide it by 9.8, and I get 11.9. So there's delta y. Now what is the velocity at the very top? Well, we said that the y component of the velocity is 0. But what is true about the horizontal component of the velocity? It's constant. It's going, what did we say it was? 12.9, so it's going 12.9 right here. It's going 12.9 right here. It's going 12.9 right here. So I can just say the velocity is equal to the velocity in the x direction. And I could just say that, well, that's the velocity is 12.9 meters per second. So I don't really need to do any computation. I just need to understand the physics. Any questions on that? Yes?
How did you know that, like, you wanted to find the velocity next?
Well, the question is, how do we know to find the velocity in the x direction? What is it asking for here? It's asking for the velocity. Now, velocity can't, what is velocity? Well, the velocity is a combination of its x component and its y component. Well, its y component is 0. The only thing that's left is the x component. And we say, oh, the velocity is just its x component because its y component is 0. So it's 12.9. Does that make sense?
Yeah.
Okay. Yes?
If it was like at a different point than like the top.
It would be different. Yes. If the question was if it was at any other point, could you do that? And the answer is no, because if you're right here, let's say you're right here, your velocity now is like this. Remember, your velocity is always tangential to your path. So it would have the same x component, would be this or this right there, the x component, but this y component is going to be, now it's going to be less than v naught y because gravity is slowing it down, but you would have to be given enough information to figure out what that velocity in the y direction is. Okay, moving on. So we got this. Now we need to know the time. Well, I'm going to use the, I need time. What do I know? I know the initial velocity in the y, and I know the final velocity in the y. I know the acceleration. I want to know time. That's the first kinematic equation. Vy equals v naught y plus a times t. So now, the final velocity in the y is 0. So I'm going to say t is equal to negative v naught y, because I'm moving this to the other side, divided by a. That's all. And so when I do this, I'll say a is equal to negative v naught y. Oh, I'm off screen. Tell me if I'm off screen. And this is what was v naught y was negative 15.3 meters per second divided by negative 9.8 meters per second squared. So a is equal to 15.3 divided by 9.8 equals. And that would be, what am I doing? That's t, I'm sorry. Hey, if I'm screwing up, feel free to, like, you're screwing up. I was testing you guys with that, and I'm sorry if you all failed. All right, and that would be 1.56 seconds. That's what I got. So it must be right. All right. Okay. Now let's do part C. We want to know delta y for the whole thing. Do I need to do any computation? No. I just need to think. Starts at this height, goes up, and ends at the same height. Y initial and y final are the same height. Therefore, delta y is 0. So we got that. Now I want to know the time, the total time. There's two ways to do it. Let's do it the long way, and then I'll show you the shortcut way. What do I know? I know delta y is 0. So I can use, and I'm solving for time. I know the acceleration. I know the initial velocity in the y direction. So let's use the third kinematic equation, which is delta y equals v naught t plus 1/2 a t squared. Oops. All right. But what do we know is true about delta y? We just said it. It's 0. Now that actually saves us a lot of work. If delta y is non-zero and you want to set, let's say you want to know how much time did it take the ball to go up and then back to here, to this height right here. If you did that, your delta y would be non-zero, and it would be possible to solve for time, except what kind of equation is that going to be? A quadratic. So you have to use the quadratic formula, or you with your fancy pants calculators could hit the solve button and get 2 answers. Why would it give you 2 answers? Because it's the time that it takes to get to this height and the time to get to, see, this, if this is your delta y right here, there's 2 times where it's at that delta y. Your first time and your second time. They'd both be valid. But since it went up all the way and all the way down, delta y is 0, thank goodness. So 0 equals v naught times t plus 1/2 a t squared. This is v naught y. I should put on an a and the y. Now, what can I do to this? I don't have to use the quadratic formula with this. Why? Because I can divide both sides by t. And this is still 0 equals v naught, but the t's cancel, plus 1/2 a, but the t cancels the t squared, 1/2 at. And now I can solve for t. So t equals negative v naught. Right, bring that over there, multiply both sides by 2, and divide by the acceleration. Let's plug in our values. Negative, what is v naught? In the y direction, it's 15.3 times 2 divided by negative 9.8 meters per second squared. Oops. And now I can get the time. So 15.3 times 2 divided by 9.8 equals 3.12 seconds. Yay. Is there a shortcut way I could have done this? What do you notice about this time and this time? Yeah, this is half the amount of time of this. Because the time it takes to go up, whoop, is exactly the same as the amount of time to come down. Woo. Because same acceleration, same change in y. All right? You're going up and you're coming back down at the same height. So that's just something you can do. You could take this time and say, okay, it's a symmetric problem, just multiply it by 2. So we got the time. Now let's do delta x. There is only one kinematic equation for delta x. Delta x equals v naught x times t. That's it. That's the only equation in the x direction you can really use for projectile motion, because there is no acceleration in the x direction. The most common mistake students make on projectile motion problems is they include 9.8 meters per second squared in the x direction. If you do that, you are saying that gravity pulls sideways. That would be a very interesting world to live in. But does it pull east, west, north, south? I don't know. So anyway, v naught x is 12.9 meters per second times, well, 3.12. So delta x is equal to 40.2 meters. That's what I got. So it must be right. Okay. So a lot to do on this problem. The problem on the test isn't this long. I'm just showing you all the things I could do with this problem on the test. Now let's do the last. So we got delta x. Well, we haven't gotten the final velocity. Notice I put a vector hat on that. Well, let's make it easy, okay? Let's make this easy. Let's draw this final velocity vector here. Now, why did I draw it like this? Well, first of all, velocity vectors are always tangential to the path. And so here's the path, so I just kind of extended that path like that. Now, let's divide it up into its components. It's got it's got a component in the x, and it's got a component in the y. Right? Now, what's true about its velocity in the x? What's its component? What is the final component of it in the x direction? Well, what's true about the velocity in the x direction for a projectile? It's constant, because there's no acceleration in the x. So this is going to be 12.9. Now, let's figure out the final velocity in the y direction. Okay. So the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration times time. So this is velocity in the y is equal to v naught y. What is v naught y? It is 15.3 meters per second. Oops. Plus, what's the acceleration? Negative 9.8 meters per second squared. And what's the time? 3.12 seconds. Okay, so let's plug our values in. 15.3 minus negative 9.8 times 3.12. And that is not the right answer. 15.3. Oh, I know what I did wrong. Plus 9.8 times 2. And there we go. That's what I wanted. Negative 15.3 meters per second. So, I mean, if you do this arithmetic, this is what you get. Is that surprising? Well, there's another way of looking at this. It goes up and it comes down. Now, what's true about delta y here? Delta y is 0. Let's look at the fourth kinematic equation. Okay, the fourth kinematic equation says Vy squared equals V naught y squared plus 2a delta y. Now, if you go up and down, what's true about delta y? Delta y is 0. So this whole term goes away. So I want to solve for the final velocity in the y direction. Take the square root of both sides. What happens when you have the square Vy equals the square root of V naught y squared? Well, what do you get when you take the square root of something squared? You get the plus or minus thingy. Now, which am I going to choose, the plus or the minus? Well, I look at the problem. This is obviously in the downward direction. So Vy is equal to negative V naught y, which is 15.3 meters per second. All right. Well, so now I can say, well, I got these, so V is equal to, well, it's got the same x and y components as this one does, so it better have the same magnitude. And what's true about its angle? Well, I could take the inverse tangent of this, but look at this. Negative 50 degrees. Why did I say negative 50? Because look, we launched it at positive 50. It went up and down. Now it's got the same components, except the y component is negative instead of positive, which means the angle is going to be negative 50 instead of positive 50. 50 degrees below the horizon instead of 50 degrees above the horizon. Oh my goodness, look at this mess. It's a very long problem. But if you understand all of this, you're not going to have any problem on the exam when it comes to projectile motion problems, because they're all easier than this one. Any final questions? Yes?
Is it safe to assume that when it's a perfect default arc, they're always the same angle?
Yes. The question is it safe to assume that the angles are going to be the same and the velocity is going to be the same, only, downward angle? Yes, if the problem has this kind of symmetry where it launches and lands at the same height. Yes?
Do we no longer have to follow the four-step procedure?
Well, there's no force in this problem. The projectile motion problems are really, they don't involve force. They really are like Unit 2 where we're talking about constant acceleration problems, except now we're moving in the x direction and the y direction at the same time. So you're correct, this won't involve the procedure. Okay, that is all.